Assalamualaikum warahmatullahi wabarakatuh. First of all, let me introduce our team. I'm Yunita Aprilia, and my team Lutfi Mursid Darmawan, Afifah Nur Khairinisa, Sofirul Solihatunisa, and Professor Dr. Eng Agus Purwanto STMT. In this opportunity, I will probably present my research with the title Synthesis and Characterization of Cobalt-Free Lithium Nickel Oxide Substituted by Aluminum Doping from Beverage Can via Solid-State Method. As we know that Indonesia has a highly potential of 11 million tons nickel resource that can support the development of nickel-rich lithium-ion batteries in Indonesia. Now, lithium metal oxides such as NMC and NCA have been widely commercialized as electric vehicle because it has a high energy density, but the cobalt content in the material is harmful to the environment, toxic and expensive. On the other hand, one of aluminum metal source often found in beverage can with the 97% of aluminum content. In this research, our team tried to lift back the high content nickel and cobalt-free lithium nickel oxide. Further research about nickel and aluminum substitution have been done by Cormier et al. With 5% aluminum to repair the thermal stability with the discharge capacity of 230 mAh per gram. Moreover, research by Kwan et al. Could press transition of nickel phase with the discharge capacity of 164 mAh per gram. The aim of the research is to create a cylindrical battery with the cathode material that has a lower cost, efficient, and eco-friendly through the extraction of aluminum from beverage can as a cation doping to repair material stability and electrochemistry performance. Here's the methodology that we use to form LiNiO battery. First is to prepare nickel hydroxide precursor and extraction process to form alumina for cation doping. The precursor were analyzed using X-ray diffractometer, scanning electron microscope energy dispersive X-ray, Fourier transform infrared, and the electrochemical performance was tested using whole cylindrical cell utilizing an 8-channel battery tester. Aluminum extraction. First, cutting the beverage can into 2 cm and then dissolve it with 18% chloride acid solution. Furthermore, precipitation was carried using ammonium hydroxide into the solution until a precipitate was formed. Dried precipitate was mashed and then sieved in 200 mass. It was calcined for 4 hours at 800 degrees Celsius to establish aluminum oxide. Nickel hydroxide synthesis. Dissolving nickel sulfate in aqueous, then natrium hydroxide and ammonium hydroxide as a chelating agent were added into nickel sulfate solution, then stirred until produce homogeneous solution with a constant temperature. The slurry was washed by warm water until pH neutral, then filtered, and the precipitate was dried in the oven for 14 hours. Dried precipitate was mashed and sieved into 200 mass until the nickel hydroxide powder was produced. Solid-state method was used to synthesize lithium nickel oxide. Lithium hydroxide with an excess 10% mole was mixed with LiNiO precursor with the variation 3%, 7%, and 10% alumina. The mixed powder was calcined for 10 hours in 480 Celsius degree and sintered in 730 Celsius degree for 16 hours under oxygen flow of 1 liter per minute. All material that complete the material characterization test will be made cathode sheet by coating the material in aluminum foil sheet to a thickness of 200 micron for each side. Cathode sheet dried into the oven before battery manufacturing. Next, roll the separator sheet between the LiNiO cathode and graphite anode to prevent contact between the two electrodes. Electrode filling is carried out in the vacuum glove box, and the final step is testing the battery. Based on GGPDS standard number 2963 data, that alumina sample has been successfully extracted from beverage can because it has diffraction pattern that form cubic structure of aluminum oxide. The latest parameter of aluminum oxide sample is 7.92 Armstrong, that's suitable with the result that has been reported by Gafurov et al. Here's the morphology particle of aluminum oxide from the beverage can extraction, distribute from 1.2 until 4.2 micron diameter particle. The EDX curve display data on the presence of metals such as 42.57% of aluminum, 47.7% of oxygen, and also certain of magnesium and carbon. Nickel hydroxide precursor also tested using SRD analysis. The sample has a beta nickel hydroxide with a hexagonal structure that has a similar diffraction pattern with the GGPDS standard number 14 and 117 data, and the result from Hall and Pu et al. With the difference of lattice parameter is 0.038 Armstrong. From the results of XRD analysis, the 4 lithium nickel oxide cathode samples shown the suitability of the peak point position at the same degree to each other, had the same intensity, and the diffraction pattern form have matched with the reference standard for the lithium nickel oxide cathode. Calculation of peak point has been obtained to determine the lattice parameter value and the coefficient R value in each cathode sample. Based on Zhu et al. Suggested that the higher lattice parameter value, the layer material arrangement is more systematic than the lower R value. In contrast, the lower R value indicates the hexagonal crystal arrangement is getting better, is overcoming the cation mixing problem that often occurred in nickel-rich cathode. Based on the results of SAM tests, the average primary particle size for lithium nickel oxide cathode sample are shown in the table. Purwanto et al. Suggests that material with the smaller particle can facilitate lithium transfer, but they provide poor electrochemical performance, while particles with the larger size provide higher specific capacities. The figure shows the result of FTIR analysis test on variation of lithium nickel oxide sample. Metal oxide regions is present in 645 per centimeter spectrum. The wavelength between 860 to 1430 per centimeter indicate the presence of nickel oxide. The LiNiO sample also shown the presence of carbonate at the peak of 867 per centimeter due to the excess lithium hydroxide content that react with carbon dioxide and then produce lithium carbonate. A peak of 1630 per centimeter indicates the presence of water, and the peak of 3630 per centimeter indicate the presence of hydroxide from nickel hydroxide group. The battery electrochemical performance test results are shown in the table. Discharge capacity show an increase along with increasing the aluminum component in the base material lithium nickel oxide. The capacity of 10% mole aluminum is higher than other lithium nickel oxide variation according to the material characterization. The lithium nickel oxide structure with the good characteristic can facilitate the lithium ion transfer process. From our research, we can conclude that aluminum oxide was successfully extracted from beverage can waste with the cubic structure that can be used for cation doping in LiNiO battery. Material active nickel-rich cathode with the variation LiNiO pristine 3%, 7%, and 10% alumina of LiNiO was successfully synthesized via a solid-state method with a layer hexagonal structure. Based on XRD analysis, result of LiNiO pristine has a good layer material arrangement but has a highly potential of cation mixing problem. Then the variation of 10 alumina LiNiO has the best initial specific discharge capacity 37.48 mAh per gram. Okay, I think enough for our presentation. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.